Hey everybody, welcome back to another round of physics, and yeah, let's get going. We have taken some time to go through some of the mathematical stuff, namely these ideas about vector fields and fluxes, and now it's time for us to kind of pull both of those together and ground it into the physics that we're doing here in this class. And that whole compilation of packaging of the mathematical ideas and applying to these physical ideas is encompassed in a phrase that is known as Gauss's law for the electric field. Now, I have this picture for you, a tragedy to be sure. Hopefully nobody was hurt. But the idea here is you've heard the adage, where there's smoke, there's fire. We can look at this house, and although we don't see the fire going on inside, we can look at the exterior of the house to understand there's some fire inside the house. Now, Gauss's law will do the same thing, except we're not talking about fire and smoke, but rather electric fields and their charges. Another example for you, if I had something like this, if I had a water bottle and it was simply pouring behind a screen and you saw no water exiting, you would say, hey, there's something behind the screen, such as a cup, something to catch the water. Or similarly, if I have some sort of screen and you see water emanating from behind the screen, yeah, you'd say, hey, there's got to be some sort of source, some sort of faucet, for example. And again, we will use that idea, but rather than thinking about water, we'll think about the electric field. Concretely, what's inside the box? And ask yourself, pause it, and say, wait a minute, not only what's inside the box, but you can start making some very generic statements. Okay? For example, is it a positive or negative charge? You hem and haw for a little while and you say, wait a minute, positive charges are what we sometimes refer to as sources of the electric field. If I go back and look at the equation for the electric field, you notice that when Q is positive, the electric field should emanate away from the charge. Whereas if I put a negative charge in, that negative usually gets associated with the direction. And so rather than emanating from a negative charge, right, it sinks towards it. Much like a faucet is a source of water and a drain is a sink, a place where water goes to. So here we notice that because the electric field is emanating from the box, we can say that there is some positive charge inside. Now, Gauss's law goes a little bit further. Here, we only said that we could find out the sign of the charge, right? Positive or negative. Gauss's law goes even further and tells us that if we can count up exactly how much, in quotes, electric field emanates from the box, that is proportional to the amount of charge inside. The rough analogy would be something along the lines of more smoke means a bigger fire. Good. So let's go ahead with that quantification. We've already talked about how flux is how much of a vector passes through an area. And previously, we just talked about some generic flux, which I labeled as U. Now, this is the math part. We will concretely use the electric field moving forward when we're talking about fluxes. Gauss, what he discovered, and we will go ahead and prove, or at least show, is that the net flux going through the surface of, for example, our box is proportional to the charge inside the box divided by a constant. And that constant, which we all know and love, is the permittivity of free space. It serves as a constant of proportionality between the amount of flux produced by a given charge. And I always like this. This is always interesting to think about because charges come in discrete packets, right? I can hand you 1 electron or 2 electrons or 10 electrons. Charge comes in discrete packets. That means that the flux of the electric field also comes in discrete packets. I hand you 1 electron's worth of charge. I am handing you 1 divided by epsilon naught units of flux, packets of flux. Let's go through and give you a sense of how you could arrive at this expression. Okay? So what I will do is let's go ahead and consider a single point charge. And what I would like to do is calculate the total flux due to this point charge. Now, how I'm going to do it is, first of all, I have to define an area. I have to define a surface through which I want to determine the flux, number 1. The second thing, this surface, I have free reign. I can choose whatever I want, but there are some good choices. And I also want to make sure that that surface completely encloses the charge. You say, why? Imagine, going back to our fire example, if I walk up to the front door, is examining the front door sufficient for determining if a fire is inside the house? You go, no, right? If I look at the front door and I say, well, everything seems to be fine there could be a raging fire going on, smoke pouring from the roof, but because I'm only looking at the front door, I'm completely oblivious to there are other places for the smoke to emanate from. So if I approach a house, not only do I have to look at the front door to determine if there's a fire inside, I have to look at the sides, maybe look through the windows. Maybe I need to go to the back door and double check that there's no smoke coming from the back door. I have to look at the roof. Right? I have to look at the entire surface of the house, not just the front door. In the same way, if I want to know the total flux generated by this charge, the total electric flux, I need to make sure that I don't leave any spot where electric field lines can escape. Well, if that's the case, I need to make sure that I fully enclose my charge so that I know that I've counted up all of the electric field. We still haven't talked about, aside from the fact that we need it completely closed, we have not talked about what makes a good surface. Well, there's 2 ideas. So we could, for example, enclose this whole thing in a box. You say, okay, well, that is certainly easy for us to think about the surface of a box. We like flat surfaces. Imagine for a second, I apologize, pretend that that charge is in the center. But there are things that make this arrangement not ideal. For example, recall that we want to calculate the total electric flux. And so to do that, we are going to need to determine the flux of the electric field through each of the 6 sides of the box. And then we will have to add those together. So you could say the total is going to be the sum of the individual 6 sides. Call that I. Well, let's just focus on the top for a second. Now, directly above the charge, the field point, so I'll get rid of the rest of these. Imagine directly above the charge, there's a field point that's on the surface, the top surface. And you say, well, what direction is the electric field pointing? You say, good, well, I haven't put in a coordinate system, but up. Okay? And so you can imagine, okay, the electric field is pointing up, right here. And I should say that is a small infinitesimal chunk of the surface, And so this is a small infinitesimal contribution to the total flux. But now let's think about, say, a corner way over here. And first of all, we say, well, what direction is the electric field? And since we have a positive charge enclosed, you would say, oh yeah, it goes away from the charge. Okay, I agree. So we should draw something like this. And now you start seeing a problem. Because I've chosen a flat surface, at different locations, the electric field is making a different angle with the surface. So if I'm thinking about my flux calculation for a moment, my flux calculation for the top surface being the electric field dotted into the area elements, I notice immediately that this dot product is going to become particularly arduous, right? The n hat is perpendicular to the surface away from the interior. And we notice that directly above, that one patch directly above the charge, the electric field and n hat are pointing in the same direction. They're parallel. Well, that's easy for that one small infinitesimal piece. But as I move around the surface of that box, the electric field points in varying directions. And so the dot product becomes a lot more difficult. But wait, there's more. Not only does the angle between the electric field and n hat vary as I choose different locations on the surface of the box, but the magnitude of the electric field also changes. Notice that this piece directly above the charge, that is the shortest distance to the charge, and I should draw my electric field as having a higher value. But the corner piece, it's further away from that charge. The magnitude of the relative position vector is larger, and so the electric field is smaller. Maybe like this. So not only do I have a problem, I have to worry about the dot product continually changing, but I also have to worry about the fact that the magnitude of the electric field changes. Now, I don't know about you, but that seems like a lot of work. Now, it's not impossible. I think that you would be able to actually do all of the calculations, but there's a better choice. Notice the choice of a box keeps n hat in the same direction, but then the magnitude of E and the direction of the electric field changes constantly. It would be nice if we could find a shape that allows the electric field to stay constant. Yeah, good. You're probably already coming up with that. Okay? The shape that keeps the electric field constant at every field point on the surface, that's not a cube. Okay? Rather, the shape that keeps the electric field constant at every field point would be a sphere. And now, because I'm considering all the points equidistant from the center charge, we can say that the magnitude of the electric field is constant. It's just kq over r squared. Notice I'm talking about the magnitude. So now the magnitude of the electric field is constant. Well, what about the direction? We should get some sense of the direction of the electric field on the surface of the sphere. And notice we'll have to take that surface of the sphere and chop it up into tiny, small area segments. Yeah, you could say, well, the electric field points in an infinite number of directions, right? For, say, this unit, that little patch is pointing this way, but it's pointing this way on that patch and this way on that patch. etc., etc., etc. Each patch has it going in a different direction. But I say, yes, there's an infinite number of directions, but we can describe that with one unit vector. Notice that every unit vector on that surface that's perpendicular to the surface points directly away from the center. And so the electric field, the normal vector for every one of those area elements is in the r hat direction. But wait, the electric field is also in the r hat direction. And so by choosing the sphere, we have taken care of two of the difficulties that we had when we tried to consider the box. Number one, the electric field stays constant. And number two, now the electric field is always parallel to n hat. And those two really help make that integration easier. Now, yes, we have to do spherical coordinates and integrate over the surface of the sphere, but the electric field is now constant. So we've traded some difficulties. I assure you this is the approach that'll be easier. So let's get at it. We would like to calculate the total flux through the surface of the sphere. And so we have to remind ourselves, okay, the mathematical definition of flux is the electric field dotted into a small infinitesimal element, and then we take the summation. Well, that's fine. Let's go ahead now and take advantage of the fact that we chose a sphere. Namely, that the electric field can simply be a constant magnitude times the r hat vector. And notice that I have altered our n hat vectors, our normal vectors, are 100% analogous to r hat again. And then we say, wait a minute, reminding ourselves of the dot product. If I have r hat dot r hat, that is equal to, good, you could say r hat squared. But by definition of being by being a unit vector, it has a magnitude of 1. And so now I don't even have to worry about vectors anymore, right? R hat dot r hat is 1. And so I can rewrite this as simply the magnitude of the electric field, which is constant. And because it's a constant, I can pull that outside the integral. And then I integrate over the surface area of the sphere. Now, I'm not going to go ahead and set up that integration for you. It's a double integral. We've done that in a previous video. That's the whole reason why I did it. And so here, we'll simply quote the results. The surface area of a sphere is 4 pi r squared. I will also go ahead and substitute in the definition of the electric field. Now, instead of having it as kq over r squared, I will actually write k out. K is 1 over 4 pi epsilon naught q over r squared. So I will write E in this sense. And now we have a goody-goody moment. We notice that I have a 1 over 4 pi times 4 pi. The 4 pi's cancel. One coming from the expression for the electric field, the other coming from the integration over the surface of the sphere. But wait, there's more. I notice that I have an r squared in the denominator. I have an r squared in the numerator. And so those also cancel out. And I'm left with the total electric flux due to a point charge is simply the value of the charge divided by epsilon naught, which is the exact relationship I showed you on the previous slide. This is Gauss's law. Now, some curious things for a moment. Notice that the final expression, even though I was calculating the flux, I chose a sphere. Notice that the final answer says nothing about the shape of the sphere. There's nothing about the radius. There's nothing about the geometry at all. The 4 pi disappears the radius disappears. There is nothing about the geometry of the surface whatsoever. Now, that's beyond the scope of this course, but what I will affirm for you is that indeed this relationship holds regardless of the surface you chose to surround your particle. So we could have done it with a box. The mathematics would be more arduous, but at the end of the day, we would have arrived at the exact same result. So you have free choice. How you decide to wrap your charge. Incidentally, this surface is often referred to as a Gaussian surface. It is, for lack of a better word, I'll put arbitrary. It is a user-defined surface through which you decided to calculate the electric flux. You have a free choice. With great power comes great responsibility. Make sure to choose a surface that makes your life easy. Good? Yeah, good. I will also highlight this is a consequence. You could say Gauss's law for the electric field is a direct consequence of the Coulomb force. Okay. In fact, it does work like that. If you take the expression for the Coulomb force to be correct, to be exact, Gauss's law for the electric field is a logical result of the Coulomb force being correct. You could flip it. We could say that Gauss's law is correct, and we would be able to rederive the Coulomb force law. Gauss's law is always true. It is not always useful. Generally, what we will do is we will calculate the flux and then use Gauss's law to determine what the electric field has to be. Okay? I'll post another example video that demonstrates that for you. We will determine the electric field due to an infinitely long line charge. And we'll actually do it two ways. Way number one, we'll do a direct integration of the contributions to find the total value. The second way is we'll apply Gauss's law. And we'll find that either way, we arrive at the same conclusion. One taking a little bit more arduous integration paths, the other being about 2 lines, maybe 3. Okay? Well, hey, I'll leave it there for Gauss's law, but again, I'll have an example video or two posted. Keep up the good work. Thanks for your attention. I'll see you next time.